The first is a picture of the normal arterial pulse. The ascending branch is relatively steep, formed by rapid ejection of blood from the ventricle. The arterial blood pressure rises rapidly, and the vessel wall is expanded. The descending branch is relatively flat. The second is when the aorta is narrowed. The ejection resistance is large. The slope and amplitude of the ascending branch are small. The third is when the aorta wall is insufficiency. The blood pressure is in the aorta drops sharply, and the descending branch is steep due to the regurgitation of blood in the aorta. Veins are the channel for blood to flow back into the heart. Because of their easy expansion and large capacity, they are called volume vessels and serve as blood reservoirs. The contraction and relaxation of veins can effectively adjust the return heart blood volume and cardiac output to meet the needs of the body and different physiological conditions. The blood pressure of the large veins in the right atrium and the thoracic cavities is called central venous pressure, and the blood pressure of the veins of various organs is called peripheral venous pressure. The central venous pressure is low. The normal fluctuation range is 4 to 12 cm. Return to the relationship between blood volume. If the heart's ability to eject blood is weakens, the right atrium and vena cava are congested, and contravenous pressure increases. The effect of gravity on venous pressure. Blood in blood vessels can produce a certain hydrostatic pressure on the vessel wall due to the influence of the Earth's gravity field. The hydrostatic pressure of each part of the vessel depends on the body position. When the human body lies supine, because the position of the various parts of the body and the heart are most at the same level, the hydrostatic pressure is also roughly the same. When the human body turns from a supine position to an upright position, the blood pressure in the blood vessels of the foot is higher than that in the supine position, and the increased part is about 80 mm each, while the intravascular pressure above the heart levels is lower than that in the supine position, such as top of the skull. The pressure in the sagittal sinus can be reduced to about -10 mm each. The effect of gravity on veins is far greater than that on arteries. Transmural pressure refers to the difference between the pressure of blood on the tube wall and the pressure of the extravascular tissue on the tube wall. Having a certain transmural pressure is a necessary condition to keep the blood vessel filling and expanding. The venous return blood volume is equal to the cardiac output per unit time, which depends on the difference between peripheral venous pressure and central venous pressure, and venous blood flow resistance. The average filling pressure of the systemic circulation. The higher the filling degree in the vascular system, the more the venous return heart blood volume. When skeletal muscle contracts, it can squeeze the vein in and between the muscles, thus accelerating the venous return. Posture changes mainly affect the veins. Transmural pressure changes back to the heart blood volume. Vein exhalation, the negative pressure of the pleural cavity decreases. The blood volume of the venous return to the heart decreases accordingly. The blood circulation between arterioles and venules is called microcirculation, as a place for the body to exchange substances and gases with the external environment. Microcirculation plays an important role in maintaining the metabolism of tissue cells and the homeostasis. The microcirculation structure includes arterioles, posterior arterioles, capillary, sphincter, true capillaries, blood capillaries, arteriovenous, anastomosis, and venules, etc. The structure and function of various organs and tissues in the body are different. The composition is also different. The composition and blood flow paths of the microcirculation are 1. Direct access arterioles, blood capillaries, venules, which are more common in skeletal muscles. The main function is to make part of the blood quickly pass through the microcirculation and enter the veins. 2. Anterior venous short circuit arterioles, arteriovenous anastomosis, venules, which are more common in the skin and subcutaneous tissues and play a role in body temperature regulation. 3. Circuit paths, arterial, posterior arterial, precapillary sphincter, true capillary, venule. This passage is tortuous, and the blood flow is slow. It is a place for material exchange between blood and tissue fluid. The blood flow of the organ is relatively stable for a certain period of time, but the flow velocity in different microvessels at the same time is very different. The reason is that the posterior arterial and capillary sphincter continue to occur every minute 5 to 10 alternating and intermittent contraction and relaxation activities called vasomotion. They control the opening and closing of capillaries. With this strength, the capillaries close, causing the accumulation of more metabolites in the tissues surrounding the capillaries. 2. Partial pressure decreases. The accumulated metabolites and hypoxia, especially the latter, can in turn cause local posterior arterioles and capillary sphincter to relax. So the capillaries open and the metabolites accumulated in local tissues are cleared by the blood stream. Material exchange is the basic function of microcirculation. Tissues and cells exchange materials with tissue fluid through cell membranes, while tissue fluids and blood exchange materials through capillary walls. Diffusion is the most important way of material exchange between blood and tissue fluid. Filtration and reabsorption, although only a small part of the material exchange, but the production of tissue fluid has an important role. The diffusion rate of solute molecules per unit of time is proportional to the difference in concentration in plasma and tissue fluid. The permeability of the capillary wall to the molecule, the effective exchange area of the capillary wall, etc., and is proportional to the thickness of the capillary wall. Diffusion distance is inversely proportional. Interstitial fluid is formed by the filtration of plasma through the capillary wall into the interstitial space and is the internal environment for cells to survive. Most of the tissue fluid is jelly-like and cannot flow freely due to the selective permeability of capillaries. Various ionic components in tissue fluids are the same as plasma. However, there is a significant difference between the potential concentration in tissue fluid and plasma. Under normal circumstances, the tissue fluid is continuously produced from the arterial end of the capillary. At the same time, a part of the tissue fluid returns to the capillary through the venous end of the capillary, and the other part of the tissue fluid flows back into the blood circulation through the lymphatic vessels. Therefore, the amount of normal tissue fluid is in a dynamic equilibrium state. The dynamic balance depends on the combined action of four factors, namely capillary blood pressure, tissue fluid hydrostatic pressure, plasma colloidal osmotic pressure, and tissue fluid colloidal osmotic pressure. Among them, the capillary blood pressure and the colloidal osmotic pressure of tissue fluid are the force that causes the fluid to filter from the inside of the capillaries, while the hydrostatic pressure of tissue fluid and the colloidal osmotic pressure of plasma are the force that cause the fluid to be reabsorbed from the outside of the capillaries to the inside. The difference between the power and the reabsorbed power is called the effective filtration pressure. The amount of fluid filtered through the capillary wall per unit time is equal to the product of the effective filtration pressure and the filtration coefficient. The size of filtration coefficient depends on the liquid permeability and filtration area of the capillary wall. The capillary filtration coefficients of different tissues are very different. The filtration coefficients of brain and muscle are very small, while the filtration coefficients of liver and glomerulus are very large. In general, 0.5% to 2% of the plasma flowing through the capillaries is filtered out into the interstitial space. At the arterial end, about 90% of the filtrate is reabsorbed at the venous end, and the remaining about 10% enter the lymphatic capillaries. the formation of lymph fluid. Under normal circumstances, the generation and return of tissue fluid maintain a dynamic balance. If this dynamic balance is disrupted, causing excessive tissue fluid production or reduced reabsorption, too much fluid will be retained in the interstitial space and form edema. Effective capillary hydrostatic pressure is a main factor that promotes tissue fluid production. The increase in systemic or local venous pressure is the main cause of the increase in effective hydrostatic pressure. The effective colloid osmotic pressure is the main force limiting the production of tissue fluid. The plasma colloidal osmotic pressure may depend on the concentration of plasma proteins, especially albumin. Under normal circumstances, the capillary wall is almost impermeable to proteins, so that the normal effective colloidal osmotic pressure can be maintained, because about 10% of the liquid filtered from the capillary needs to flow back through the lymphatic system. Whether the lymphatic system is unblocked can directly affect the tissue fluid backflow. That's all for this lesson. Thank you for your attention. See you later.